Hey guys, welcome back to another video. And this is going to be the last video in this series that is for gravitational fields. And in this video, we're going to talk about astrodynamics. This is actually sort of my favorite topic, and this is something in general I do want to study about eventually. So what this talks about is, first, let's understand the energy of different objects due to its position in the gravitational field. Now, the thing is, for all the planets out there, it tends to orbit around, let's say, a star or a planet. In case of Moon, it is orbiting around Earth. In case of Earth, it is orbiting around Sun, right? Everything turns out to be orbiting around something. So it has a certain velocity. Therefore, it has a certain kinetic energy. However, it is also under the influence of gravitational field of the object around which it is revolving, right? So in case of Earth, it's revolving around Sun, right? In case of the satellite we talked about in geostationary object video, the satellite is orbiting around Earth, right? Therefore, every object over here has a certain kinetic energy, and it has a certain gravitational potential energy due to the gravity acting on it. And there's an interesting question that how can you escape the gravitational field of any planet, any star? The easy answer to it is give it enough kinetic energy. If you give it enough kinetic energy, it will break free of the gravitational field strength and be away from the gravitational fields. The gravitational fields will no longer have any effect over the planet, over the object, over the mass, because it has enough kinetic energy to escape from it. And in case of that kinetic energy, it needs a certain velocity, which is known as escape velocity. So those are the things we're going to understand through different parts in this video. First up, we're going to understand the kinetic energy of satellites, right? Now, we know from previous videos that V square is equals to Gm by R. If you don't know where that came out of, here's the quick recall of it. So basically, in case of a satellite revolving around Earth, its centripetal force is provided by the gravitational field or the gravity of Earth, right? The gravitational force. Now, in that case, the centripetal force mv squared by r is provided by the gravitational force. Now, we want to understand or know the speed of, the orbital velocity of the satellite. So what we do is use this formula of centripetal force and make v squared or v the subject. So what we get from there is v squared is equal to gm by r, right? Now, to find the kinetic energy of the satellite, what we can do is we know the formula of kinetic energy, that is half mv squared, and you know the value of, or the expression for v squared, that is gm by r. Plug that in over here, and what you're going to have is ke is half times gm m by r, right? Fair enough. So that is its kinetic energy. Now, let's figure out its gravitational potential energy due to its position in the field of Earth. In that case, we're going to have minus g m m by r. This is the gravitational potential energy of the satellite. Now, can you notice something interesting over here? That is, the kinetic energy is exactly the half of the potential energy, the gravitational potential energy. And this is actually going to be quite useful later on in this video. So what both of these figures mean is, if I have this object rotating, revolving around Earth, it has a certain kinetic energy, half gm m by r, and its potential energy, meaning the work done that was needed in bringing this pink object from infinity to this point was minus gm by r, right? From infinity to this point, I needed minus gmm by r worth of work done to bring it from that point to over here. Therefore, if I want to do the opposite and take it from this orbit or from this position near the Earth's surface or near the Earth to infinity, I need to provide positive gmm by r. How will I do that? I will, let's say, do extra work on it. I'll provide it with my energy. I'll provide it with my energy and provide the exact amount as gmm by r, such that it will go to infinity. And at infinity, the potential energy or the field strength of Earth is going to be 0 because it is infinitely away. Therefore, at that point, no field strength, therefore no gravitational potential energy. Therefore, it is free of Earth's gravity, right? It has escaped Earth's gravity. So let's work with that idea. So we can figure out the total energy of the satellite at this point. It has this kinetic energy and this potential energy. So the ET, that means E total, is going to be half gmm by r minus gmm by r. What that results in is the total energy of the satellite is minus gmm by r, or you can write it as minus half gmm by r. What does this mean? That means it does not have enough kinetic energy. Remember, half gmm by r. Gmm by r, right? So it does not have enough kinetic energy for the satellite to move away or get out of the gravitational fields of Earth. It does not have enough energy. In the case that its kinetic energy was exactly gmm by r, it could have escaped, because in that case, positive gmm r plus negative gmm by r would give you E total of 0. In that case, it would have escaped from Earth's gravity, because the net energy on it, its net energy would have been 0. That means it is under no one's influence. It is under no one's influence, right? Fair enough. So now, if I plot the energy on the y-axis and I plot the distance on the x-axis for the kinetic energy, notice it is positive. It is on the positive axis and it decreases with increasing distance, because notice the gravitational field strength would decrease. Since the satellite is in orbit, its centripetal force is provided by the Earth's gravity, right? Therefore, in the case that it oscillates, I keep saying oscillation. So in the case that it is farther away, if this was its initial orbiting circle, if it went farther away, that means the field strength at that position is less. Therefore, its kinetic energy would be less as well. Its kinetic energy would be less as well, because its speed would decrease. It would oscillate as it would orbit at a slower speed, right? Which is why its kinetic energy would decrease. Therefore, with increasing r, K decreases. Now, in case of, notice its potential energy is actually supposed to be a bit over here, around about here. Yeah. So it has double amount of the kinetic energy, right? If the satellite has exactly half gmm by r, it will have negative gmm by r. So double the amount of kinetic energy, but it is negative, right? Why negative? We have discussed it previously, right? So it is unable to escape, at the end of the day, Earth's gravity or Earth's gravitational fields. However, in the case that we had a gravitational potential energy of minus half gmm by r, what we would have is a straight line. Because notice, this yellow curve would cancel out this pink curve. And in that case, the net energy on the satellite would be 0. However, since we have this red curve, which denotes minus gmm by r, therefore a more negative gravitational potential energy, that means it is unable to escape Earth's gravitational field, right? Now, how do we make the satellite escape Earth's gravity? In that case, as mentioned, the Ke needs to be equal to gravitational potential energy. Therefore, the change in gravitational potential energy, that is, if this is the object, this is Earth, this is the satellite, and this is infinity. For the object to go from this position to infinity, its change in gravitational potential energy needs to be equal to its change in kinetic energy. Meaning, it needs to have enough kinetic energy, half mv squared, such that it provides the energy that it can work against the gravitational fields, that is attractive. It will work against those fields, against all odds, and it will be free. Therefore, that change in gravitational potential energy that the object goes through in going from near the Earth's surface to infinity, it needs to be equal to its kinetic energy. Therefore, your change in kinetic energy is half mv squared, and your change in gravitational potential energy is going to be 0, because at infinity it is 0, minus gmm by r, because near the Earth's surface it is minus gmm by r. So at the end of the day, you get half mv squared is equals to gmm by r. So ultimately, to find the escape velocity of the satellite, if you make v the subject, it turns out to be v squared is 2gm by r. So v is root 2gm by r. This v is your escape velocity. If the satellite has this velocity, it will escape Earth's gravity. If the satellite has this velocity, it will escape Earth's gravity. Okay, so in our case, what happens is the orbital speed of the satellite is actually lower than this v, or this escape velocity, which is why the satellite never gets to escape Earth's gravity. This entire video has such an interesting plot line. I mean, there's a satellite wanting to leave Earth's gravity, and it is unable to, cross all odds and be able to escape all this negative energy. Anyways, coming back to the topic. So we know the velocity, the escape velocity that the satellite needs to be able to be free from Earth's gravity or Earth's gravitational fields. But we know it will never be able to achieve that. However, we can find out the kinetic energy it needs, because we know the velocity it needs, right? So we know the formula for Ke, that is half mv squared. Velocity is root over 2gm by r. So if we plug that in, Ke turns out to be gmm by r. So as discussed over here, towards the beginning. Right, towards the beginning over here. If the Ke was exactly the same as the gravitational potential energy, it would be able to escape, right? Therefore, if your Ke is gmm by r, that is exactly equal to the gravitational potential energy, the object can finally escape, right? So that is it for astrodynamics. That is all that you need to know about for gravitational fields. And that will be it for this series. I'll try to solve a few question papers and see you in the next video.